January 1943. The frozen marshlands south of Leningrad. Snow falls in thick curtains across a landscape torn apart by 2 years of siege warfare. The temperature hovers at -20 degrees Celsius. In this desolate theater of the Eastern Front, where millions have already perished, Soviet soldiers from the 63rd Guards Rifle Division advance cautiously through a recently abandoned German position. They move between blackened tree stumps and shell craters filled with ice. The silence is broken only by the crunch of boots on frozen ground and the distant rumble of artillery. Then, through the white haze, they see it. A massive steel beast sitting motionless in a clearing, its long gun barrel jutting forward like an accusation. The tank is bigger than anything most of these men have ever seen. Its boxy turret and thick angular hull seem almost alien compared to the sloped profiles of Soviet armor. This is a Tiger. The soldiers approach with weapons raised, expecting ambush or booby traps. But the German crew is long gone, the machine abandoned intact after becoming mired in the soft ground beneath the snow. One soldier climbs onto the hull and peers through an open hatch. Inside, the smell of oil and cordite still lingers. The controls are labeled in precise German script. The ammunition racks are empty, but the mechanical components appear undamaged. This is an extraordinary prize. Within hours, word reaches higher command. Within days, engineers arrive with recovery equipment. Within 2 weeks, this captured Tiger, tracked and catalogued as Vehicle Number 2, 50122, is loaded onto a flatbed rail car and begins a long journey eastward, away from the front, toward a place where its secrets can be laid bare. The train carries its cargo through the vast Russian interior, past ruined villages and hastily constructed factories, past columns of troops moving toward the front and columns of refugees moving away from it. The Tiger rides in silence, covered with tarps to conceal it from prying eyes and German reconnaissance aircraft. Its destination is Kubinka, a proving ground located roughly 60 kilometers southwest of Moscow at the Scientific Research Institute of Armored Forces Technology, known by its Russian acronym NIIBT. The Soviet Union's best military engineers and metallurgists gather to dissect, measure, test, and ultimately understand the most formidable tank then operating on any battlefield. What they will discover over the coming months will reshape Soviet armor doctrine, influence the development of new weapons, and reveal not just the strengths of German engineering, but also its growing weaknesses as the Third Reich's industrial capacity begins to buckle under the weight of total war. The story of how the Soviets came to capture and analyze the Tiger cannot be separated from the broader arc of the Eastern Front itself. When Operation Barbarossa began in June 1941, the Wehrmacht's panzer divisions carved through Soviet defenses with shocking speed. German tanks, though not necessarily superior in armor or firepower to the best Soviet designs, benefited from superior tactics, better coordination, and often better crew training. The Soviet armored force was caught in the midst of reorganization, its commanders purged, its doctrine confused, its newest tanks dispersed in small packets among units that barely understood how to use them. The early encounters were catastrophic. Thousands of Soviet tanks were lost in the opening weeks, many abandoned due to mechanical failure or lack of fuel rather than enemy action. But as the war ground on through 1941 and into 1942, the Soviets learned quickly. They consolidated production around a few proven designs, especially the T-34 medium tank and the KV-1 heavy tank. They improved logistics and crew training. They adapted their tactics to emphasize massed attacks and the exploitation of mobility, and they began to inflict serious losses on German armor. By late 1942, the Wehrmacht found itself facing an opponent who could replace losses faster than Germany could, who fielded tanks with sloped armor that deflected German shells, and whose industrial base, though battered and relocated beyond the Urals, was beginning to outproduce the Reich's factories. It was in this context that Adolf Hitler demanded a new generation of German tanks, vehicles so heavily armored and powerfully armed that they could restore battlefield dominance through sheer technological superiority. The Tiger Thesuace, designated Panzerkampfwagen 6 OAF E, was the result. Development began in 1941, accelerated after encounters with the T-34 and K-1 shocked German confidence. The Tiger entered production in August 1942 at the Henschel factory in Kassel. It was a radical departure from previous German designs, where earlier Panzers emphasized mobility and mechanical reliability. The Tiger prioritized firepower and protection above all else. It mounted the formidable 88mm KWK-36 gun, a weapon derived from the legendary Flak 88 anti-aircraft gun that had proven devastating against Allied tanks in North Africa. The Tiger's armor was unprecedented, 100mm thick on the front of the hull, 120mm on the turret face. Even the side armor measured 80mm, thicker than the frontal armor of most Allied medium tanks. But thickness alone does not tell the full story. The true strength of the Tiger's armor lay in its material composition and manufacturing quality, details that would only become clear once Soviet engineers could examine an intact specimen. Throughout 1942 and early 1943, Tigers began appearing in small numbers on the Eastern Front, usually concentrated in elite independent heavy tank battalions. Their impact was immediate and terrifying. Soviet tank crews reported hits that simply bounced off Tiger armor at ranges where Soviet guns could normally penetrate German commanders, filed reports of Tigers surviving dozens of hits in a single engagement. The psychological effect was profound. The Tiger became a legend, feared and respected, its reputation sometimes outpacing its actual battlefield performance. Yet the Tiger was also rare. Germany's industrial capacity, stretched thin by commitments on multiple fronts, could produce only about 1,500 Tigers over the entire war. They were expensive, complex, and mechanically temperamental. Each Tiger required enormous quantities of strategic materials, especially molybdenum, nickel, and chromium for its armor steel. And as the war progressed, these materials became increasingly scarce. But in early 1943, when Soviet engineers finally obtained their intact specimen, these problems were still in the future. The Tiger they would examine represented German armored manufacturing at or near its peak. The captured Tiger arrives at Kubinka in February 1943. The proving ground is a sprawling complex of test ranges, workshops, and laboratories, surrounded by birch forests and connected to Moscow by a single-track railway line. The facility is always busy, testing captured German equipment alongside new Soviet prototypes. But the arrival of the Tiger generates unusual excitement. Engineers gather around the rail siding as the tank is unloaded. Some have seen technical intelligence reports or grainy reconnaissance photographs, but seeing the machine in person is different. It is massive, weighing 56 tons, nearly 20 tons heavier than the KV-1. The vertical armor plates are precisely welded, the joints clean and uniform. The road wheels are interleaved in an overlapping pattern that distributes weight more evenly than conventional suspension. The craftsmanship is immediately apparent. The initial inspection begins the same day. Engineers measure every external dimension, photograph every detail, and compile a complete inventory of components. The hull is 9.5 meters long, including the gun, 3.7 meters wide. The tracks are 725 millimeters wide, necessary to keep ground pressure reasonable despite the immense weight. The turret traverse mechanism is hydraulic, powered by the engine, allowing relatively quick target engagement for such a large vehicle. The gun itself, the 88mm KWK 36L/56, is examined with particular interest. Soviet intelligence already knows this weapon is extraordinarily effective, but measuring its chamber dimensions, rifling, and breech mechanism provides data that will inform future Soviet gun development. The engineering team assigned to the Tiger examination includes some of the Soviet Union's most experienced armor specialists. Among them is Colonel Engineer Nikolai Fedorovich Shashkov, a veteran of the Red Army's technical services, who has spent years studying captured German equipment. Shashkov oversees the systematic disassembly of the Tiger's major components, ensuring that every part is catalogued, measured, and photographed before being sent to the appropriate laboratory for detailed analysis. His methodical approach will set the standard for how captured enemy equipment is evaluated throughout the remainder of the war. Working alongside Shashkov are metallurgists from the Central Research Institute for Ferrous Metals, specialists who understand the complex relationship between alloy composition, heat treatment, and armor performance. These scientists have been studying armor steel since the early days of the war, analyzing fragments recovered from battlefields, comparing Soviet and German manufacturing techniques, and searching for ways to improve Soviet armor production. The intact Tiger represents an unprecedented opportunity to examine German armor in its original condition, free from the distortions caused by battle damage. But the real investigation begins when engineers start removing armor plates for metallurgical analysis. The welding alone is worthy of careful study. German welders used manual arc welding techniques with electrodes specifically formulated for high-strength steel. The welds are deep, with full penetration through the plate thickness, and show consistent bead profiles. There is minimal spatter, few inclusions, and the heat-affected zones adjacent to the welds show proper grain structure under microscopic examination. This level of quality requires not just skilled welders, but also careful preheat procedures and controlled cooling rates, techniques that demand time and resources. Soviet wartime welding, by contrast, often prioritized speed over perfection, sometimes resulting in weaker joints and stress concentrations. The Soviet engineers note that German welders apparently preheated the armor plates to approximately 200 degrees Celsius before welding, then maintained that temperature throughout the welding process. After welding, the assemblies were allowed to cool slowly, sometimes in insulated boxes, to prevent the formation of brittle microstructures in the heat-affected zone. This attention to thermal management reflects a sophisticated understanding of metallurgy and a willingness to invest significant time in each vehicle's construction. The Soviets calculate that welding a single Tiger's hull and turret probably required several days of work by highly skilled craftsmen, a luxury that Soviet factories, producing dozens of tanks per day, simply could not afford. The armor plates themselves are sent to the Institute's metallurgical laboratory, where they are cut into samples, polished, etched with acid to reveal microstructure, and examined under optical microscopes. What the metallurgists find is remarkable. The steel is rolled homogeneous armor, meaning it was formed by hot rolling an ingot into plate form, which aligns the grain structure and improves toughness. The alloy composition includes approximately 0.3% carbon, 1% manganese, 3% nickel, 1.5% chromium, and critically, about 0.3% molybdenum. This combination produces steel that is both hard enough to resist penetration and tough enough to absorb impact energy without shattering. Molybdenum, in particular, is the key. This element, when added to steel in small quantities, dramatically improves hardenability, meaning the steel can be effectively hardened to greater depths during heat treatment. It also refines the grain structure and increases resistance to tempering, allowing the armor to maintain its properties even after exposure to the heat generated by shell impacts. Molybdenum was expensive and difficult to obtain, sourced primarily from mines in Norway after Germany occupied that country in 1940. The presence of molybdenum in Tiger armor is a clear indicator of the priority Germany assigned to heavy tank production in the early war years. The heat treatment process used on Tiger armor is equally sophisticated. After rolling, the plates were heated to approximately 850 degrees Celsius, then quenched in oil to rapidly cool the surface. This creates a hard outer layer resistant to penetration. The plates were then tempered or reheated to a lower temperature, around 400 degrees Celsius, to reduce internal stresses and increase toughness. The result is armor with a hard face to resist shell penetration and a tough core to prevent cracking. Soviet metallurgists document this carefully, noting that the surface hardness measures approximately 260 to 280 on the Brinell scale, while the core hardness is slightly lower, around 240 to 260. This gradient is intentional and effective. The Soviet scientists are particularly impressed by the uniformity of the heat treatment across large plates. Achieving consistent hardness over a plate measuring 2 meters by 1 meter requires precise control of furnace temperature, quenching bath conditions, and cooling rates. The Germans appear to have used purpose-built quenching tanks with agitation systems to ensure uniform cooling, along with careful temperature monitoring throughout the process. The tempering operation, which reduces brittleness while maintaining hardness, was similarly controlled. This level of process control indicates that German armor manufacturers were operating with sophisticated equipment and well-trained personnel, advantages that would become increasingly difficult to maintain as the war progressed. With the metallurgical properties understood, attention turns to ballistic testing. The Soviets are eager to determine exactly what weapons can defeat Tiger armor and under what conditions. A series of firing trials is organized at Kubinka's ballistic range. Sections of the captured Tiger's armor are mounted on test frames, and various Soviet anti-tank weapons are fired at them from measured distances. The results are methodically recorded: weapon type, ammunition type, impact angle, range, penetration or failure, and observations of armor behavior. These tests will generate data that informs Soviet anti-tank tactics and weapon development for the remainder of the war. The testing protocol is rigorous. Each weapon system is tested multiple times at various ranges and impact angles. The armor samples are carefully positioned to simulate the angles they would present in actual combat. Targets representing the frontal hull are set at 0 degrees from vertical, matching the Tiger's actual armor configuration. Side armor targets are positioned to simulate a 90-degree approach angle, as well as various oblique angles that might occur in combat. High-speed cameras record each impact, allowing frame-by-frame analysis of how the armor responds to shell strikes. Technicians measure crater depth, crack propagation, and spalling on the back face of penetrated plates. The first tests use the standard Soviet divisional anti-tank gun, the 76mm ZS-3. This weapon, firing armor-piercing shot, strikes the 100mm frontal plate at a range of 500 meters. The shell hits with a sharp crack and engineers rush forward to examine the impact. The armor is barely dented. A shallow crater marks the impact point, but there is no penetration, not even a crack. Multiple shots from the ZIS-3 produce similar results. At shorter ranges, under 300 meters, some shells manage to dig deeper, but full penetration remains elusive. The conclusion is stark. The Soviet Army's most common anti-tank gun cannot reliably defeat the Tiger's frontal armor under typical combat conditions. The test results with the 76mm gun are sobering, but not entirely unexpected. Soviet commanders in the field have already reported the inadequacy of this weapon against Tigers, but seeing the scientific confirmation at Kubinka drives home the scale of the problem. The ZIS-3, which has proven highly effective against earlier German tanks like the Panzer III and Panzer IV, is simply outmatched by the Tiger's armor thickness and quality. The engineers document that even at point-blank range, under 100 meters, the 76mm gun achieves only marginal penetration against the frontal plates, and even then, only if the shell strikes perpendicular to the armor surface. Next comes the 85mm gun, used on the newly developed T-3485 tank and the D-5T gun mounted on some KV-85 prototypes. The 85 fires a heavier shell at higher velocity. The results are better, but still disappointing. Against the frontal hull at 500 meters, the 85mm achieves occasional penetrations, but only when the impact is perfectly perpendicular. Any angle, even slight, causes the shell to ricochet. Against the turret face, with its 120mm of armor, the 85mm simply cannot penetrate beyond 300 meters. The Soviets realize that even with upgraded guns, their medium tanks will struggle against the Tiger in a frontal engagement. The ballistic tests with the 85mm reveal something else important. The quality of Tiger armor causes shells to shatter more frequently than expected. When an 85mm armor-piercing round strikes Tiger frontal armor at an oblique angle, the shell often breaks apart rather than ricocheting intact. The hard surface layer of the German armor, combined with its toughness, creates conditions that place enormous stress on the penetrating projectile Soviet armor-piercing shot of this era, made from medium carbon steel that is through-hardened, lacks the resilience to survive such impacts. The shells fracture into fragments that scatter harmlessly away from the tank. This discovery will eventually lead to improvements in Soviet ammunition design, including the development of armor-piercing rounds with softer caps that cushion the impact and protect the penetrator core. The situation changes dramatically so when they test heavier weapons. The 100mm BS-3 anti-tank gun, though not yet in widespread production, proves capable of defeating Tiger frontal armor out to 1,000 meters with consistent reliability. The 122mm, a 19-core gun, a powerful field piece sometimes used in an anti-tank role, smashes through Tiger armor with shocking violence. At 500 meters, the A-19's shell doesn't just penetrate, it blows massive chunks of steel off the back face of the plate, sending fragments flying across the test range. The sheer kinetic energy of a 12-kilogram projectile traveling at 800 meters per second is simply too much for the armor to absorb. The tests with heavy-caliber weapons provide crucial validation for Soviet weapon development decisions. The 122mm gun, in particular, demonstrates such overwhelming effectiveness that it becomes the clear choice for arming the next generation of Soviet heavy tanks. Engineers calculate that the A-19 and its tank-mounted derivative, the D-25T, possess more than enough energy to defeat Tiger armor even at extended ranges, and with a comfortable margin that accounts for variations in ammunition quality and combat conditions. The dramatic overmatch also means that even if the Tiger's armor quality improves, or if thicker armor is encountered, the 122mm gun will remain effective. The side armor tells a different story. At 80mm thickness, it is still formidable by the standards of most tanks, but it is significantly more vulnerable than the frontal protection, the 76mm ZIS-3, which failed against the front, can penetrate the side at typical combat ranges, especially if the shell strikes at a favorable angle. The 85mm gun defeats the side armor reliably under almost any practical combat scenario. This discovery has immediate tactical implications. Soviet tank commanders are briefed: do not engage a Tiger from the front unless you have overwhelming numerical superiority or heavy weapons support. Instead, maneuver to attack the flanks. Use terrain, smoke, and coordinated attacks to get around the Tiger's frontal arc. Accept losses in the approach if necessary, but get to the sides. The rear armor is even more vulnerable than the sides, measuring only 80mm on the hull rear and 80mm on the turret rear. Soviet tests confirm that virtually any anti-tank weapon in the Red Army inventory can penetrate the Tiger from behind. This knowledge reinforces the importance of combined arms tactics. Infantry anti-tank teams, armed with PTRD anti-tank rifles or RPG-43 anti-tank grenades, are briefed to attack Tigers from behind. Whenever possible, artillery observers are trained to coordinate indirect fire to suppress Tiger positions, while tanks maneuver for flank shots. The systematic understanding of Tiger armor vulnerabilities transforms what had been a terrifying, invincible opponent into a target that can be methodically defeated through proper tactics. As the testing continues through the spring and early summer of 1943, Soviet engineers compile a comprehensive technical report on the Tiger tank. The document runs to hundreds of pages, including detailed drawings, photographs, metallurgical data, and ballistic test results. Copies are distributed to tank design bureaus, artillery designers, and senior military commanders. The report becomes a foundational text, referenced in countless meetings and design reviews over the following years. But the investigation at Kubinka does not end with the first Tiger. Throughout 1943 and 1944, additional Tigers are captured as the Eastern Front shifts westward. Each new specimen is examined, and patterns begin to emerge. One particularly valuable capture occurs in July 1943. During the Battle of Kursk, Soviet forces overrun a German tank repair facility and capture several damaged Tigers in various states of disassembly. These vehicles provide insights into Tiger maintenance requirements, component longevity, and common failure modes. Soviet engineers discover that the Tiger's interleaved road wheel system, while providing excellent weight distribution and a smooth ride, is prone to accumulating mud and debris that freezes solid in winter conditions. The complex transmission, with its 8 forward gears and sophisticated steering mechanism, requires frequent maintenance and is vulnerable to breakdowns if not serviced by skilled mechanics. These operational weaknesses are documented and disseminated to Soviet commanders, who learn to target Tigers during winter operations when mechanical problems are most likely. By late 1943, Soviet metallurgists notice something troubling in the newer Tigers. The armor quality is declining. Samples taken from Tigers captured in the autumn show different alloy compositions. The molybdenum content has dropped, sometimes to as little as 0.1% or even absent entirely. In its place, German manufacturers have substituted vanadium, another alloying element that improves strength but does not provide the same combination of hardness and toughness that molybdenum offers. The heat treatment on these later plates also appears less consistent, with wider variations in surface hardness and more evidence of quenching cracks. The reason for this decline is clear. Germany is running out of molybdenum. The strategic materials shortages that began to bite in 1943 are forcing compromises throughout German industry. Molybdenum supplies, dependent on Norwegian mines and increasingly disrupted by Allied bombing and resistance activity, cannot meet demand. German metallurgists are doing their best to maintain armor performance with substitute alloys, but the results are inferior. The vanadium alloyed steel used in late production Tigers is harder on the surface, sometimes measuring up to 300 on the Brinell scale, but it is also more brittle. Under heavy impact, this armor is more prone to catastrophic cracking, where the entire plate fractures rather than simply being penetrated. Soviet engineers test this new armor and document the difference. A plate from a late production Tiger, struck by a 122 mm shell, develops a massive crack that spiders across more than half the plate's surface. The same test on an early production plate resulted in a clean penetration hole with minimal cracking. The late-war armor, for all its surface hardness, fails more dramatically because it lacks the internal toughness to absorb impact energy. This discovery has a demoralizing effect on Soviet assessments of German industrial strength. If the Germans, with all their engineering expertise and industrial tradition, are being forced into such compromises, then perhaps the Reich's material position is worse than previously estimated. The degradation of German armor quality is not limited to changes in alloy composition. Soviet metallurgists examining late-war Tigers also detect problems with the manufacturing process itself. Some plates show evidence of inadequate heat treatment, with hardness values that vary significantly across the surface. Others exhibit poor surface finish, with roughness and irregularities that suggest rushed machining or worn tooling. Weld quality declines as well, with more frequent defects like porosity, incomplete penetration, and irregular bead profiles. These problems reflect the broader deterioration of German industrial capacity under the combined pressures of Allied strategic bombing, labor shortages, and resource scarcity. The knowledge gained at Kubinka influences Soviet weapon development in concrete ways. The decision to arm the new IS-2 heavy tank with the 122 mm D-25T gun rather than the 100 mm D-10T is partly based on the Tiger armor tests. Soviet designers know from empirical data that the 122 mm gun can reliably defeat Tiger frontal armor at combat ranges, while the 100 mm gun, though offering a higher rate of fire, provides a narrower margin of effectiveness. The 122 mm becomes standard, and the IS-2 enters mass production in early 1944. When IS-2s encounter Tigers in combat, Soviet crews have confidence in their weapon, a confidence born from the scientific testing conducted at Kubinka. The IS-2's development is closely monitored by Joseph Kotin's design bureau, which has been working on heavy tank designs since before the war. Kotin and his team visit Kubinka multiple times during 1943 to observe the Tiger tests and consult with the engineers conducting the analysis. They take detailed notes on the Tiger's strengths and weaknesses, using this information to refine the IS-2's design. The decision to mount the 122 mm gun, despite its lower rate of fire compared to smaller calibers, reflects a clear understanding that defeating heavy German armor requires overwhelming firepower. The IS-2 is specifically designed as a Tiger killer, and the Kubinka test data provides the empirical foundation for its combat effectiveness. The Tiger armor analysis also influences Soviet metallurgical practices. Seeing the quality of German welding and heat treatment, Soviet industry makes efforts to improve its own processes. New welding training programs are established. More attention is paid to preheat and cooling procedures. Some Soviet tank factories begin using improved electrode formulations that produce stronger welds. The impact is incremental rather than revolutionary, constrained by the demands of mass production and the need to prioritize quantity over perfection. Soviet tanks will never achieve the manufacturing precision of German vehicles during the war, but the gap narrows. By 1944, Soviet armor plate quality has improved measurably, and weld failures become less common. Soviet metallurgists also apply lessons from Tiger armor to improve their own steel formulations. While the Soviet Union cannot match German access to molybdenum and other alloying elements, Soviet researchers experiment with alternative compositions that can achieve acceptable performance using more readily available materials. Some success is achieved with silicon-manganese steels that, while not as effective as molybdenum alloyed armor, provide better performance than simple carbon steels. The heat treatment protocols used in Soviet armor production are also refined, with more attention paid to quenching rates and tempering temperatures. These improvements, though modest compared to the quality leap represented by German armor, contribute to the overall effectiveness of Soviet tanks in the war's final years. There is a broader lesson in all of this, one that Soviet engineers and commanders internalize as the war progresses. The Tiger tank represents a particular philosophy of armored warfare, that a smaller number of superior vehicles can dominate a larger number of inferior ones through sheer technological advantage. This philosophy requires a robust industrial base, access to strategic materials, and the luxury of time to manufacture complex machines. Germany possessed these things in 1942 and early 1943, but by 1944, all three were in decline. Soviet doctrine, by contrast, emphasized mass production of simpler, more reliable vehicles that could be manufactured quickly and repaired in the field. The T-34, though individually inferior to the Tiger in armor and firepower, could be produced in vastly greater numbers and operated by crews with less training. The ballistic tests at Kubinka quantify this trade-off. Yes, a single Tiger can defeat multiple T-34s in a frontal engagement, but if 10 T-34s attack a Tiger from multiple directions, accepting the loss of several tanks to get side shots, the Tiger will be destroyed. And while Germany can produce 1,500 Tigers over the entire war, the Soviet Union produces over 50,000 T-34. The mathematics of attrition favor the Soviets, but only if Soviet commanders are willing to accept heavy losses and employ proper tactics. The knowledge gained from studying Tiger armor helps refine those tactics, teaching Soviet crews exactly where and how to strike. Soviet tactical doctrine evolves throughout 1943 and 1944 to incorporate the lessons learned from Tiger analysis. Tank brigades receive specific training on encountering heavy German armor. Crews practice coordinated attacks where multiple tanks engage a single target from different directions simultaneously. The importance of combined arms coordination is emphasized, with tank attacks supported by artillery fire, smoke screens, and infantry anti-tank teams. Radio communications improve, allowing better coordination during battle. Tank commanders are taught to identify Tigers at a distance by their distinctive profile and to immediately call for heavy weapon support when Tigers are spotted. The psychological dimension of facing Tigers is also addressed through training and indoctrination. Soviet tank crews in 1943, especially those who have experienced the terror of seeing their shells bounce off Tiger armor while their own tanks are destroyed at long range, sometimes develop a fatalistic attitude when tigers appear. This tiger fear, as some Soviet officers call it, can paralyze units and lead to poor tactical decisions. By disseminating accurate information about tiger vulnerabilities, by training crews in effective anti-tiger tactics, and by providing tanks armed with weapons capable of defeating tigers, Soviet commanders work to restore their crews' confidence. The knowledge that a tiger can be killed, that it has weak points, that it is not invincible, makes an enormous difference in combat effectiveness. By the time the war reaches its final year, the Tiger I is being supplemented and eventually replaced by the even heavier Tiger II, known as the King Tiger. This vehicle mounts thicker armor and a more powerful gun, but it also suffers from mechanical unreliability and fuel shortages. Soviet forces encounter King Tigers in combat, and additional specimens are captured and sent to Kubinka for analysis. The pattern repeats: detailed examination, metallurgical testing, ballistic trials. The engineers at Kubinka become the Soviet Union's leading experts on German armor, their reports eagerly awaited by field commanders and designers alike. The King Tiger analysis reveals that Germany's material problems have worsened significantly by late 1944. The armor quality is noticeably inferior to early war Tigers, with brittle fractures occurring even under moderate impact. The welding shows numerous defects. Some plates exhibit visible warping from improper heat treatment. The King Tiger is a powerful vehicle in theory, but its construction quality has been compromised by Germany's collapsing industrial situation. Soviet engineers note these problems with grim satisfaction. The technological advantage that Germany sought through heavier and more complex tanks is being undermined by the same industrial exhaustion that affects all aspects of the German war effort. The final Soviet offensive operations of the war, from Operation Bagration in the summer of 1944 through the drive on Berlin in 1945, benefit from the accumulated knowledge of German armor capabilities. Soviet anti-tank units know which weapons to deploy against heavy tanks. Tank crews know which angles of attack to avoid, and which to seek. Artillery commanders know that concentrating fire from heavy guns on known Tiger positions can neutralize them before they engage Soviet armor. This knowledge does not make Tigers harmless, but it makes them less terrifying, reduces their psychological impact, and turns them into problems that can be solved through proper application of firepower and tactics. The Battle of Berlin in April 1945 provides a final demonstration of how Soviet understanding of German armor has evolved. Tigers and King Tigers are deployed in the city's defense, positioned in fortified strongpoints and hull-down positions that maximize their defensive advantages. But Soviet forces, now veterans of 3 years of combat against German heavy armor, methodically neutralize these positions using combined arms tactics, heavy artillery pounds, suspected tank positions. IS-2s engage Tigers at ranges where the Soviet guns' superior penetration is decisive. Infantry anti-tank teams infiltrate through rubble to attack from behind. The Tigers fight hard, but they are overwhelmed by an enemy that understands their capabilities and knows how to counter them. After the war ends in May 1945, the work at Kubinka continues. The proving ground becomes a repository for captured German equipment of all kinds. Dozens of German tanks, including Tigers, Panthers, and King Tigers, are preserved there, some kept in running condition for comparative testing against new Soviet designs, others disassembled for training purposes. The metallurgical data gathered during the war forms the foundation for post-war Soviet armor development lessons about alloy composition, heat treatment, and welding practices inform the design of the T-54 and later Soviet tanks. The institutional knowledge built up during the war years becomes part of the Soviet military-industrial complex's DNA. The engineers and scientists who conducted the Tiger analysis become senior figures in post-war Soviet weapons development. Colonel Engineer Shashkov continues his work at NIIBT through the 1950s, overseeing the evaluation of captured Western equipment during the Korean War and later conflicts. The metallurgists who examined Tiger armor apply their expertise to developing improved Soviet armor steels, eventually contributing to the development of composite and reactive armor systems in later decades. The ballistic specialists who conducted the firing tests establish protocols that remain in use for decades, ensuring that Soviet tank designs are thoroughly tested before entering production. The Cold War era sees renewed interest in the Tiger studies as Soviet designers work to counter American and British heavy tanks. The M103 heavy tank and British Conqueror are analyzed using many of the same techniques developed during World War II. The lessons about armor quality, manufacturing precision, and the relationship between material properties and ballistic performance continue to inform Soviet military engineering. The institutional memory of how the Tiger was understood and defeated becomes part of the broader Soviet approach to military technology. Assessment. The captured Tiger at Kubinka, vehicle number 25012-2, survives the war and remains at the proving ground for decades. It is eventually restored and displayed at the Facilities Museum, now known as the Kubinka Tank Museum, one of the world's most extensive collections of armored vehicles. Visitors can walk around the Tiger, peer through its vision ports, and marvel at the thick armor plates that Soviet engineers once subjected to such intense scrutiny. The tank sits silent now, its secrets long since revealed, but it remains a testament to a particular moment in technological and military history. Modern historians and military analysts continue to study the Soviet Tiger analysis as a case study in technical intelligence and weapons assessment. The methodical approach taken by Soviet engineers, the rigorous testing protocols, and the systematic dissemination of findings to operational units represent best practices in understanding enemy capabilities. The Tiger studies demonstrate how scientific inquiry can be effectively integrated with military operations, how knowledge can be weaponized as effectively as steel and explosives, and how understanding an enemy's tools contributes to defeating the enemy itself. The story of how Soviet engineers came to understand Tiger armor is not a story of a single breakthrough or a dramatic moment of discovery. It is a story of methodical, painstaking work conducted under wartime pressures by skilled professionals determined to extract every possible advantage from a captured enemy machine. It is a story of metallurgists peering through microscopes at polished steel samples, of welders examining seam profiles, of ballisticians calculating impact angles and penetration depths. It is a story of knowledge gained through scientific inquiry and applied through tactical doctrine, weapon development, and industrial improvement. In the end, the Tiger's armor was defeated not by a single wonder weapon or brilliant tactical innovation, but by the steady accumulation of understanding combined with overwhelming material superiority. The Soviets learned exactly what the Tiger was, how it was made, what it could withstand, and where it was vulnerable. They learned how German manufacturing quality declined as the war progressed, how material shortages forced compromises, and how even the most sophisticated engineering could not overcome strategic exhaustion. And they used that knowledge to help grind down the Wehrmacht's armored forces in a brutal campaign of attrition that stretched from the gates of Moscow to the ruins of Berlin. The Tiger tank entered the war as a symbol of German technological prowess, a machine that embodied the Third Reich's confidence in its engineering superiority. It left the war as evidence of Germany's limits, its vulnerabilities, and ultimately, its defeat. The Soviet engineers who studied the Tiger at Kubinka played a small but significant role in that outcome. They transformed a fearsome weapon into an understood problem, and in doing so, they contributed to the larger effort that brought the war in Europe to its conclusion. The armor that once seemed impenetrable was measured, tested, analyzed, and finally comprehended. And with that comprehension came the knowledge needed to destroy it. The Tiger, for all its formidable qualities, could not survive the industrial might and scientific determination of an enemy that refused to be intimidated by steel and fire.